Cool. Okay. So this is a quick kind of presentation um of my final project for ENPM818J or real-time operating system. So I implemented a real-time position I guess let's just change that. Position control. Real-time position control of a brushless DC motor. Yeah. So, the team, it was just me. I'm an aerospace engineering master's student. I like space robots, I like human spaceflight, and I like human and robot collaboration in space, if you could guess. Cool. So the mission statement for this project is we wanted to control the position of a hobby grade brushless DC motor. Uh, I think the hoverboard motor can count as hobby grade because it's not super fancy, but it's a beefy thing. So we wanted to control the position of it. So some of our mission level requirements were we need a fast control loop to implement the PD controller. We needed to track the position of the motor, so we have an encoder. We needed to use a brushless DC motor and also a brushless DC motor driver. And here are the some of the reasonings for these requirements are a PD controller or even a PID controller needs to run at a relatively fast rate for good tracking of the motor system. Um, you also need a position sensor to read where the position of the motor is, or else you wouldn't really be able to command it. I mean, you could, but if you wanted to use a PID controller, you need that input at the very least. You need a physical actuator to drive the system. So if we wanted to make an actual servo, we need to actually have a motor. And that's what the brushless DC motor is for. And they're also more challenging to work with than a brushed DC motor, which is why I wanted to use a brushless one because it was more challenging of a project. And then we also needed a motor driver to convert the command signals to phase current cycles. Basically, we needed a way to convert voltages or like digital commands to actual current. And while developing one was originally the idea for this project, it was kind of out of scope, so we left it out. We as in, well, it's just me. Well, yeah. Uh, so we have some system level requirements, which are a little lower level than the mission ones. We want a control loop that can run on the order of 1 kilohertz. So just a general generic control loop to run at that speed. Uh, we wanted the ability to read the encoder pulses at a frequency of around 10 kilohertz, and that's because with initial testing, we saw that just kind of shaking the encoder back and forth, we saw that it could reach up to 10 kilohertz frequency, and our motor isn't supposed to be moving super fast, but we need the ability to generate a pulse width modulated signal because that is what gets sent into the motor driver. We need ability to send out digital outputs fast because we need to command a direction pin. And then we also need to control, we need a circuitry for a control input, so a potentiometer in this case. And the reasonings for these requirements are PID controls needs to run at a high frequency for stable and smooth control, which we kind of touched on in the mission requirements. So it can't just run at 10 hertz or 1 hertz. Even 100 hertz is kind of low for it. I mean, you could get motion out of these, but you have so much error between your two systems that you're going to struggle to get good tracking. A high resolution encoder generates a lot of pulses, faster than what a normal while loop on just the ESP32 or even interrupt services can sometimes handle. So having a dedicated way to read in pulses is good. Uh, we needed a higher frequency PWM signal allows us to control the motor a lot smoother. So we could have done like a 1 kilohertz PWM signal generator, but it just would have been a lot more jittery and maybe not. It may be a lot more louder on the motor side. We need to be able to control direction, which I mentioned, which is what the digital output's for, and it needs to be able to do it as fast as possible. And then at least as fast as the actual control loop. And then we needed a user input to demonstrate the motor control. So here's the final system. You can see there's some 80/20 holding up the system, the power supply, the motor, all that kind of stuff, and the wiring that goes with it. On the very left is the system. On the middle is kind of a close-up of the actual motor and encoder setup. And then on the very right is how the motor is actually mounted. Because this is a hoverboard motor, the whole thing spins. That tire metal casing actually spins rather than only some of it or part of it or the shaft spinning. So while you can spin the shaft, all the wires will spin with it. So we spun the entire system which which had a lot of I think inertia, or the system has a lot of inertia because it's basically a flywheel. Uh, Here's some pictures of the electronics, which are crudely thrown together. Um, the potentiometer circuits on the left, and then the motor driver circuit is on the right. So some of the core components was this motor driver, which is a three-phase brushless DC motor driver that takes a PWM input. The hoverboard motor was a core component. I was given a broken hoverboard and I ripped apart the motor, so that's how I got that. 8020 was used to build the structure, and it allowed for kind of a modular system where we could adjust the height of the encoder and the distance of the encoder so that we can actually get ru- relatively stable connection, because none of it's very precise in terms of where the encoder should be mounted. And then, of course, we have the ESP32 and then the quadrature encoder. Um, cool. Some additional components were the Wago connectors that you saw in a couple slides back. Um, Down here is some. So these were really useful for connecting wires together. Um, Pretty much that's all I mean, they're probably useful for a lot of other things, but really I use them to connect wires together. The breadboard was used for the digital signals. We had a 30 volt, 10 amp power supply, which is driving the entire system. Um, an enable and disable switch, so it's a physical switch that I can turn on and off, and that allows me to either enable the motor or disable the motor. A potentiometer to command the motor to a certain position, and then a C clamp actually holds the motor in place. So kind of rough setup. So our PWM frequency we set at 20 kilohertz, which computed to a max duty cycle of 248 bits. So that means we can send 0 up to 248, and 248 represents our highest frequency. And we had a resolution of 1 bit, so we could do 0 or 1 or 2 or 3, and the outputted PWM signal should reflect that. Our PID control loop, we got to 1 kilohertz, so that was nice. I had some trouble going from 100 hertz to 1000 hertz. I didn't realize it was a setting I had to change, but I did change the setting and it started running at 100 or 1000 hertz, so that was nice. Our PD controller gains, I didn't spend a lot of time tuning, but I did try to tune it as best as I could. It was interesting. I was oversaturating it by having like a KP of 10, so the motor would just be super fast and always be at its max duty cycle. But going to lower gains, lower than 1, actually kind of helped smoothen out the motion. It's still a little jittery though, and I believe that's because of I think both the potentiometer jitter and the velocity, the derivation of the position jitter. So our control input is running at 100 hertz, and our data logging is running at 10 hertz, and I'll get to that in the next slide. So our main control task, we have 3 tasks. Our main control task is on an entirely separate core these priorities are wrong. Um, with a priority of 10, although it shouldn't really change anything because there's no other tasks running on that core. And the other 2 tasks are running on the current slide. The other 2 tasks are running on the first core or the 0th core, and the input control task, so what reads in the potentiometer, is running with a priority of 5, and the data logging loop runs with a priority of 1. So ideally, the potentiometer should take precedent and preempt the data logging because the data logging is only worried about um, logging data. And something I didn't mention actually in the code overview video that's going to be somewhere co-located with this is that the mutex or the mutex semaphores that I'm using to um, lock the shared buffers has a 0 wait time. So if for some reason the input control task wants to write to the command buffer, but the data logging task is using the command buffer, the input control task will not block. It'll just rerun and keep generating control until it gets lock. And I think that's better because it just will keep the command to whatever the last value was until it gets a new updated one. And although that might have a big discontinuity from the previous to the next, I think it's better than having the system block. But yeah. And then, of course, there is an accompanying video of me going over the code, and then the GitHub write-up has a bunch of more information about the system and not just the system requirements. So, yeah, thank you so much.